Now, hydrocarbons are broadly divided into aromatic carbons and aliphatic hydrocarbons. Now, basically, aliphatic hydrocarbons are further divided into cyclic and acyclic hydrocarbons. Now, acyclic, these are basically, okay, let's come here. Aromatic hydrocarbons are benzene and its family. Benzene and its family. So this is benzene. Benzene and its family. Now, today we are not discussing aromatic hydrocarbons, but now we are going to be streamlining our discussions to where we find alkenes. And basically, we have a subdivision of acyclic hydrocarbons into our key discussion for today, alkenes, and then we have alkynes. Now, these basically are single bonded alkenes. They are straight chain alkenes, number one, and they are singly bonded. Now, alkenes are double bonded, while alkynes are triple bonded. So you have a carbon-carbon double bond, carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond. But today, like I said, we'll be streamlining our discussions to alkenes. So this is the class where we have alkenes. Now, under cyclic hydrocarbon, the first member of this group is cyclopropane. Cyclopropane is the first member. As I discuss alkenes or acyclic alkenes, of course there are still cyclic alkenes. Those are the ring form alkenes. We'll be discussing the ring form alkenes, this group also. We'll be discussing this group in combination with this group. But then our basic discussions will be centered around alkenes. Alright. So we have tried to give a classification of alkenes. We will now try to go into another concept. Now, I have already told us that alkenes are single bonded and they have a general formula. So we consider the general formula of alkenes. And the general formula of alkenes is given as CN H2N plus 2. This is for the alicyclic hydrocarbons or alicyclic alkenes. Now, so this is alicyclic alkenes or acyclic, let's say. Call it alicyclic, acyclic hydrocarbons. So this is the basic formula. Now, that of cyclic alkenes is given as CnH2n. So this is for cyclic alkenes. Now, note this. The formula for cyclic alkenes also corresponds with the formula for alkenes. I mean, acyclic alkenes, straight chain alkenes. The formula for cycloalkanes is always the same for the formula for straight chain or acyclic alkanes. So probably in our further studies in organic chemistry, I will still point out this to us. Now, having known their formulas, we can actually use these formulas to develop the members of alkanes. For example, the first member of the alkane series is called methane. So it's a first member, so the number 1 is attached to methane. And so when we put in 1 as an integer into this equation, we will get C1 H2 into bracket 1 plus 2. So this gives us CH4. This gives us CH4. So this basically is the first member of the alkane series. Now, on this note, we are going to get the first 10 member of the alkane series because this will form our foundation for further studies in organic chemistry. So it is important, as at your 100 level or 200 level, you should have known the first 10 members of the alkane series, because you'll be working and playing with them. So if you don't know it from now, it becomes an issue. So having talked about this, we are going to talk of the first 10 members of the alkane series, and these are their names, and then you have the molecular formula. So you have their names and the molecular formula. So let's try to make a line here. Names, molecular formula. So the first member of the alkane series is methane, and then the second member is ethane, the third member is propane, the fourth member is butane, the fifth member is pentane, the sixth member is hexane, the seventh member is heptane, the eighth member is octane, the ninth member is nonane, the 10th member is decane. So now these are the first 10 members. Now we will now try to get the molecular formulas of all the first 10 members of the alkane series. So now the first member here, as it is, using this formula, we've been able to get the first member. So this is actually the first member of the alkane series. So we put in 2 here, which corresponds to 18. We should be able to get the second member of the alkane series. So you have CH4 as a molecular formula for methane. Now, the second member of the alkane series is CH3, CH2, CH3 again. Of course, if you put in 2 here, you get C2. So this is our carbon, first carbon, this is second carbon. If you put in 2 here, you will get 2 times 2, 4 plus 2, which is 6. So we now have, now it's written in this form because, of course, from our studies in hybridization, if you have not watched that video, I will tell you to make a referral to my discussion on hybridization. I said carbon does not exceed 4 bonds. Carbon is tetrahedral in nature and it always has 4 bonds. So in attempting to draw this structure in a way that carbon will assume that bonds of 4, we now make it in a way that there are 3 hydrogens around carbon here. Of course, the 4th bond is going adjacent to this carbon. So you see that this carbon has 4 bonds, this carbon has 4 bonds. Further on, as we go into naming in organic chemistry, I will explain this more better for us. So now our propane will be CH3, CH2, and CH3. Our butane will be CH3, CH2, CH2, CH3, CH3, CH2, 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 CH3, CH3, CH2, 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 CH3, CH3, CH2, 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 CH3. We have CH3, CH2, 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 and CH3. We have CH3, CH2, 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 CH2. We have 1, 2, 3, 4, 5, 6, 7, 8, CH2, and then CH3. Okay, we're adding an extra one, so we now have CH3 here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So one must go again to make us have 9. So that's CH3. Now this is CH3, CH2, 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 CH3. So these are the first 10 members of the alkene series. These are the first 10 members of the alkene series. So it's good you familiarize yourself with this now. Peradventure you forget the number of hydrogens or the number of carbons are supposed to be there. You refer back to the formula we have here. That's a formula that it's perfect. So whenever you impute the number, for example, nonene it's number 9. So when you put in 9 into that formula, you should be able to get the number of hydrogens and the number of carbons you should find in nonene. So this is a very easy way of trying to arrive at the members of the alkene series. Now, another important thing we are going to discuss are the alkyl groups. The alkyl group. We are discussing this because it will help give us a foundation in nomenclature. So, to be able to be conversant or to be good in naming alkanes, which is our next topic, we should try to get ourselves familiarized with alkyl groups. Alkyl groups are like the branches you will see when trying to name alkanes. So that when we get there, it's not going to be a difficult thing for us. Now, the alkyl groups. Now, alkyl groups are a very important group in the alkane series. They are very important, and it is important for us to know that you get alkyl groups by the loss of one hydrogen. When an alkane loses a hydrogen, it gives rise to an alkyl group. So, for example, methane is CH4, that's methane. When it loses an hydrogen, what does it give rise? It gives rise to a methyl. So I'll tell us the principle surrounding this. Now look at it. This is methane. Methane is CH4. Now when it loses an hydrogen, it turns to CH3. Of course, the structure of methane is this. This is the structure of methane. So you see that it loses an hydrogen, so there is a bond that is waiting. Now, most likely, alkyl groups are attached groups, or they are attachment groups. So they are always attached somewhere. Why? Because they've lost hydrogen and they need to get attached somewhere to be stable. Remember, I told you that carbon is tetrahedral and will always want to have 4 bonds to be stable. So they are unstable groups. You can call them an unstable group. So whenever they loses an hydrogen, they want to attach themselves somewhere. So you always see them as branches while doing nomenclature in organic chemistry. So now this name is now gotten from, of course, you saw the name alkenes. The removal of ANE and a corresponding addition of YL will give rise to alkyls. So therefore, in naming alkyls, you will remove the corresponding ANE from that alkene, and you add YL to get a corresponding alkyl group. So for example, when we remove ANE from methane that have lost one hydrogen and add YL, it gives rise to what? Of course, methyl. So it's that simple. So whenever we can form more alkyl groups, this is the first member of the alkyl series. So you have methyl. For example, we have ethane. So if we have ethane, that's the possibility of having methyl, of having ethyl. So this is an ethyl. You remove ANE and you add YL. So the structure now becomes CH3, CH3. So instead of having CH3, CH3, what are we going to have here? Of course, it's CH3, CH2. But there must be a bond going off from the structure to tell you that this is an unstable bond. This is an unstable compound, number one. Number two, this compound is not saturated yet. It has lost one hydrogen. So it's eager to attach itself somewhere. That's why I told you that they are always attached somewhere. They are unstable. So they always want to react. They always want to go into reactions. Do you understand that? So that is why wherever they are found in reaction, they always look for a way to attach themselves somewhere. So this is the concept. Now we can go on and on getting other members of the alkyl series. So we have methyl now, we have ethyl, we can have propyl, we can have butyl, we can have pentyl, we can have hexyl, we can have heptyl, we can have nonyl, we can have octyl, we can have nonyl, which is carbon number 9. So nonyl, instead of C9H20, we are going to have C9H19. So that is it. That is nonyl for you. Then you can have decyl as well. So these are the members of the alkyl series. Subsequently, it will make sense when we go into nomenclature. We'll try to now understand how these alkyls come into play. And when we go into reactions of alkanes also, we will really understand the role they play in organic chemistry. Now, we will discuss an important concept and then we call it a day for this lecture. Now, we'll try to understand branched alkanes. Try to understand the concept of branched alkanes. Now, we have the first member of the alkane series as methane, the second member of the alkane series as ethane, the third member as propane, and the fourth member as butyl. Now, it is important for us to know that in drawing out the structure of the first three members of the alkane series, which is this is methane, this is the first member, this is the second member, this is ethane, and this is propane. You'll find out that there is no other possible way you can arrange these three structures as to get another different structure. There is no other way you can arrange these three structures as to get another different structure. So, where that arrangement starts, in order for you to get a different structure from the initial structure, still bearing the same number of carbon, it's carbon number 4. So therefore, we'll come to the concept of isomerism. Positional isomerism starts from butane. It is important because you will actually see this in your MCQs, your objectives, and then possibly can come out as a theory to write on isomerism. So it is important to know that isomerism starts from butane. That is a way of arranging that structure in a way as to get a different structure with a different name. So isomerism is the ability of a compound to have the same molecular formula but different structural formula. So we are going to demonstrate it with butane. Now, for butane, of course, we all know that butane has a carbon number 4. So this is butane. Now, this is the normal butane, so we call it N-butane. The normal structure of butane, that's the meaning, N-butane. So, an isomer of butane will be a different structure from butane. Though it have, now the molecular formula is C4H10. The second structure will definitely have the same number of carbon because we have 1, 2, 3, 4 carbon. The number of hydrogen is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the second structure we are going to be drawing will have C4H10, but then it will be a different structure. Now let's try to put on our straight chain 3 carbon only. If we do that, we'll now have 1 hydrogen here, the second hydrogen here, the third hydrogen here, the fourth hydrogen here, the fifth hydrogen here, the sixth hydrogen, the seventh hydrogen. Now, instead of putting our hydrogen here, this will give us propane. We'll put in a carbon here. Now you see that we have a fourth carbon. And then we put our 8th hydrogen here, the 9th hydrogen here, and the 10th hydrogen here. We can see clearly that these structures are different. In structure they are different, but then these structures still have a molecular formula C4H10. So that is to tell you that this is an isomer. Now in nomenclature, when we get to nomenclature, I will tell us why this is named this, but the name of this is a branch, so we name it 2-methyl propane. 2-methyl propane. This is a hyphen. 2-methyl propane. Now, don't bother about this name. If you're confused on how I named it, just calm down and I go into nomenclature. Of course, this will be the easiest for you. But then, we should know that this is the name of this, while this is normal butane. So you see, in nomenclature, they bear different names because their structure differ, but they are isomers. So this 2-methyl propane is an isomer of butane. So you can be asked, what is the isomer of butane? The only isomer of butane we have is 2-methyl propane. 2-methyl propane is the only isomer of butane. So there are only 2 isomers of butane, which is the N-butane and then 2-methyl propane. So now we can still talk about another member of the alkane series. We'll talk about pentane, for example. Now, pentane has a normal structure 1, 3, 4, 5. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have C5, H12. Now, the first isomer of propane will be like this. You will see the same, so the molecular formula here is C5H12. So therefore, we can draw another structure having the same molecular formula, but it's bearing a different structure. So this is H here, 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 this other one, and then you have hydrogen here, and then hydrogen here. Now we can see that there are 5 carbon here and there are 12 hydrogen, but then it is not the same in structure as it. So this is an isomer of pentane. So we call this 2-methyl-butane. 2-methyl-butane. So this is named 2-methyl-butane, and it is an isomer of pentane. Another isomer of pentane you can have is this. This is another isomer of butane. Now, so we can see that this is having 5 carbons. We have 1, 2, 3, 4, 5 carbons. So we have C5, and the number of hydrogen is 3 here, 6, this is 9, and this is 12. So we have H12. So you can see that they all have the same molecular formula but different structures. This is called 2,2-dimethylpentane. 2,2-dimethylpentane. I've told you once that you should not bother about the nomenclature for now. When we go into nomenclature, you're going to get a renewed mindset of naming, and this will be the easiest part of chemistry for you. But for now, just flow as we go. Don't bother about the name. This is 2,2-dimethylpentane. That is the IUPAC nomenclature of this structure, and it is another isomer of pentane. So pentane as a structure has 3 isomers. It has 3 isomers. So they are different. There are 3 different ways you can configure pentane to have different structures of that same molecular formula. Now, at this point, we are going to be drawing the curtain for today. I believe I've been able to give us a better understanding on the introduction of alkanes, and I believe in my next video I should be able to broaden your understanding. At this point, bye for now.